All right, in this lesson, we're going to be starting section 5.3, which is on solving trigonometric equations. We're going to break this into two parts. The first part we'll probably spend a couple of days on on its own. So we're going to be doing this for the better part of a week before we move past it and expect you to be an expert. So to get started, as a warm-up, what I'd like you to do is graph this system of equations. You'll notice it's a pretty simple system. One of them's a trig function. One of them is just y equals 0. And then I would like you to solve it graphically. So solving the system, of course, means find out where they intersect. All right, so in order to do this, since I'm using my graph more than just an illustration and actually need to use it to find an answer, I better do a decent job here. All right, let me try using, let's see if bigger squares how big will they be? That's pretty big. I'll stick with my usual. All right, so let's start by graphing the trig function. We should recognize that it is simply a regular sine graph moved down, but stretched vertically by a factor of 2. So I'm going to stick with my typical, and my typical usually means I'm going to go 2 boxes for every pi over 2 because my period has not changed. So my period of 2 pi is broken up into 4 parts. So 1, 2, 3, 4. There's negative 2 pi. I'm going to have every box be a half this way, or 2 boxes is 1. And I think I'm ready to go. I'm graphing sine moved down 1. So that means this is my new sort of center line. It is not an asymptote, of course. So I'm moving sine down and just stretching it. Okay, so this should be pretty straightforward. My new center line is here. Sine starts at 0, 0. Goes up 2. And remember, in my world here, that would be 4 boxes. So that's going to get me all the way up here to positive 1. So I'm going to go up 1, 2, over pi over 2, back down pi over 2, over to pi over 2, another pi over 2, and down 2 more. I'm going to keep going. Keep going this direction. 2 boxes here, 2 boxes here, 2 boxes here. All right, not last one. That was silly. Here. All right, so I'm just going to connect a lot of parabola-looking shapes. Some of you are really doing a fake job of your curves, and you're making it more like little triangles. Please make sure you're rounding your curves. All right, solve the system graphically. Well, it's going to be a tricky one because my answers appear to be not at very obvious spots. Doesn't mean I couldn't maybe be more detailed in my graph, but it looks like if I graph y equals 0, I sort of skip that step, right? But y equals 0, of course, is just the original x-axis. And so my intersection points all seem to be, and there's a lot of them, right? And that's not unsurprising. In fact, there are 2 every period, right? So if I look at from 0 to 2 pi, which my clicker was working. So starting at 0 and going to 2 pi, which ends here, I've got 2 places where it's 0. So every period I've got a couple of answers. All right, let's take a look. We're going to leave it right there. I know kind of where the answers are. I just don't know what they are with that level of detail. Let's do part B, and let's go ahead and graph this one. So this one should be theoretically a little bit easier because I'm just graphing normal sine. And so I start at 0, go over pi over 2, up 1. I'll add my scale in just a second. Two boxes, two boxes, two boxes. Pretty straightforward. Got my nice curves. All right, when does y equal a half? That's the graph of a half. Well, it's time to put my labels in. I'm being very sloppy. Pi over 2. This, of course, is 1. This is -1. Pi over 2. Here's 2 pi. So there's 1 period. Here's -2 pi. All right, y equals a half would be the horizontal line at a half. All right, so where are my answers? I appear to have an answer just past 0 and a little bit before pi, a little bit past 2 pi, a little bit before 3 pi. And if you notice, those are the same x values that I got in the previous graph, or I should repeat, they appear to be the same x values. So, graphically speaking, solving a system of equations is great, but in this case did not lead to very specific answers without a more specific graph. So how else can we solve a system of equations? We can solve them using substitution. So what would substitution look like on part A? It would probably be me just plugging in a 0 for y, right? And what would it look like over here? It would probably be me plugging in a half for y. So that brings us to what we're here to discuss, of course, which is, let me, hold on, a little bit of language we need to learn, and then we'll get to today's lesson. So what do we have here? We have, translate this mathematical sentence. All right, so first of all, this symbol right here means for every. We know this symbol is an element of, is a member of the set, right? However you want to think about it. But the way you read this is for every x that is an element of, or for every x that belongs in the set of numbers between 0 and 2 pi. All right, so example 1, solve the equation 2x minus 1 equals 0. And part A, I want you to find all the answers x between 0 and 2 pi. Notice it includes 0 but not 2 pi. So what is this equation? That is just what we did up here graphically. So graphically speaking, I said graph 2x minus 1 and graph y equals 0. Find out where they equal each other. In other words, find out when does 2x minus 1 equal 0. In other words, this is me just asking you to find the x-intercepts of the graph. You can see that there are 2 every time the wave passes, does one full revolution. And so if we go on forever, we're going to have an infinite number of x-intercepts. So what we're going to talk about today is how to find those and then how to answer the question. So here we go. So graphing didn't work very well. So now let's find it another way. So long story short, we're just going to do algebra here. So if I'm going to solve, I'm going to get rid of the graph paper now. If I'm going to solve 2 sine of x minus 1 equals 0, I'm just going to do algebra to get x by itself. I see 3 things that I have to deal with. I have to deal with the -1, I have to deal with the 2, and I have to deal with the sine because I want to get x by itself. So showing very basic steps, which I probably don't need to show. My first step, of course, would be to add 1. So now I have 2 sine of x equals 1. My next step would be to divide by 2, just like I would algebraically. Move the term first, and then get the variable by itself by dividing, right? So I have sine of x equals 1/2. Now, sticking with our algebra theme, what is the step I take that makes the sine disappear? I know the answer is not to divide by sine because that doesn't make any sense. Sine is a function. We have to undo the function. So technically speaking, what I have on this side is take the sine, the inverse sine of the left side, and take the inverse sine of the right side. In other words, I get it down to x equals, because inverse sine cancels out sine, equals whatever this answer is right here. And now, since this is something I'm aware of, arc sine of 1/2, I'm now probably going to consult my unit circle, unless you have it memorized, which you should at this point. What angle, right? This is what I'm asking. What angle, that's the answer, has a sine of 1/2? And the answer would be pi/6. Where else, because look at what I'm asking, where else is there an answer between 0 and 2 pi? And so I got one answer there, and I've got one answer here. So this would be another pi/6 reference angle. So this would be 5 pi/6. So theta of pi/6, that would be opening up to here, and then 5 pi/6 opens up to there. So solve the equation for all the x's between 0 and 2 pi. So the only places between 0 and 2 pi would be, I guess this is x, not theta, x equals pi/6, or x equals 5 pi/6. Okay, let's go back and look at our graph and see if that kind of matches what we've got. We had said it's a little bit after pi, so that's your pi/6, or after 0, excuse me. And we said it's a little bit before pi, which would be 5 pi/6. The reason I had you do both of these was just because I wanted you to kind of see that ultimately, this was the question that was asked, part A, but what did I really end up answering was what part B is, right? Because if you look down here, what we ultimately had was we got it down to this, but that's going to answer the same question as the original. And that's why the answers line up. Okay, so then let's look at part B and what it's asking. So now it's saying answer the question again. So do 2 sine x minus 1 equals 0. But this time I want you to give me all of the x's that exist in the universe that answer this problem, not just some arbitrary once around the circle situation here. So graphically, we saw that happen. We saw there were lots of times when that sine graph crossed over the 0. So this time what we got to do is figure out a way to answer it. Okay, so we've already done all the same work, so I'm going to not waste our time. We got it down to answering this question, right? X equals the arc sine of 1/2. So there are two ways of doing this, and some of you are hanging on by a thread, and I expect one way will make as much sense, but some of you are doing quite well, and I think we can give a better answer. So if the most rudimentary way to answer this question is, well, there are 2 times every time I go around a circle that I have a sine of 1/2. One of the answers, as we said a second ago, was pi/6. So how do we say then to get all of the other answers that are in the same location as pi/6? Well, if we go around the circle again. So if I add 2 pi to that, I'll get another answer. So there's, right, one answer was pi over 6. So let's keep track. One answer was pi over 6. A second answer might be pi over 6 plus 2 pi. A third answer might be pi over 6 plus 2 pi plus 2 pi. A fourth answer would be pi over 6 plus 2 pi plus 2 pi, and then let's go around again. So I could do this for an infinite number of times. I could do this n number of times. So notice what we have here. We've got a little pattern forming. We went around, we got to pi over 6. For my second answer, I added a 2 pi. For my third answer, I added another 2 pi. For my fourth answer, I added another 2 pi. So here's what I'm going to write. I just need to keep adding 2 pi's. So I'm just going to add an n to the end of this. But wait a minute. Looking at my problem here, if I looks like I have one less 2 pi than the number of terms we have, right? Well, the way we're going to answer that is we're going to add some disclaimers about what n is. I'm going to throw the disclaimer on here. I'm going to use I'm going to use a colon, which is the word such that n is an element of, and then I'm going to write a fancy z. My fancy z is looks like this. If I had a better typeface, right, it kind of, sometimes they'll have this, like, instead of having it thicker, they'll just double it up in the middle. That looks awful. So ultimately speaking, usually the way I draw it is I'll draw a line, I'll draw a normal z, and I'll just slightly extend this and then make the middle a little bit thicker. Okay, and that reference is, let me get rid of all these. Let me redo this one because I don't like that I thickened all of it. Still don't love that z. This is the set of all integers. And by saying this, and by the way, we could, let's introduce, let's take away such that, even though that works. Let's go ahead and use for every instead. All right. Now, again, I'm showing you the best way to do this, like the mathematical way. Some of you are not going to be mathematical people. Like you're not going to go on to be math majors and so on. That's fine. If you want to write in English what we're saying here, you can do that. But honestly, this is not that hard to figure out. So let's back up to the important part. The most important part is this first piece. That's sort of a non-negotiable. We need this. So what is the answer? We start at pi over 6, and then we add circles. How many circles do we add? Well, we're going to add all the circles. N could be 0 because we're saying n is an integer. So n could be 0, and if n is 0, then I'm adding no 2 pi's, right? So it's just pi over 6. If n is 1, I'm adding 1 2 pi, 2, 3, 4. So the n is telling you how many times to wrap around the circle. But don't forget, we can also go in the negative direction. So instead of writing plus or minus, we don't need to do that because the n could be a negative number. And so that would make it negative 2 pi. Okay, so we can wrap around the circle either direction and end up in the same spot. All right, all of this is half the answer because we had another answer. The other answer was we could also go to 5 pi over 6, and then we could wrap that one also around the circle a bunch of times. How many times? Well, any number of times that represents an integer. So these two answers together would answer the question. All right, probably this is fine for most of you. You might be a little bit intimidated by this last part, but that last part is sort of like just a stamp that goes on the end of all of these. for all the ends, because you've just told me the ends. So wrap around 2 pi n times. And then like, oh, well, what's an n? Oh, it's just an integer. N is an integer. That's all you're telling me. Okay. So in English, you could just say where n is an integer. And I suppose you could say all integers because, again, I want all of the answers. All right. But again, that first chunk is the important piece. All right. So everybody who's kind of like, oh, dear God, I hope I pass this class, you can kind of tune me out now. For all of you that are like, hey, I'm shooting to learn as much as possible, let's take a look at this and answer it maybe with one statement. So is there any way that I can say what I have here? Like, how can I identify these two locations on my unit circle and just make one of these statements? And the answer is going to come from really seeing if you can, well, what's the best way to say this? The best way to say is just do it and then see if you have any questions. So what I'm going to notice is that pi over 6 and 5 pi over 6 are uniformly, they are reflections across the y-axis. The y-axis being pi over 2. So I'm noticing that compared to pi over 2, one of the answers is pi over 3, that direction, because pi over 6 plus pi over 3, 30 plus 60 is 90. And one of the answers is pi over 3 this way. So if I'm just looking for a way to describe what the answers are, I could just say it with one statement. I could say, oh, I'm looking for all the angles that fit into, start at pi over 2, and then add a pi over 3, or subtract a pi over 3. So that alone gives me the answer of pi over 6 and 5 pi over 6. So that right there settles it at 5 pi over 6 or pi over 6. But then I can say, and then from those two spots, you can now wrap around a full circle over and over again forever. And so that would be the best answer, but at least at the beginning level, right now, I'm comfortable accepting the separate answer. All right, let's see if we can expand upon this. Let's keep going. The real trick is to see the algebra hidden in the system. So we look at example 2, part A, and I'm again trying to get x by itself. And I can see that there are two functions I need to deal with. One of the function is the squared function, and one is cosine. So what I'm going to do to start, let me rewrite the problem, is I'm going to take the square root of both sides. And of course, when I take a square root, we introduce a positive and a negative. And the square root of 1 is 1, and the square root of 4 is 2. Now I need to get rid of cosine, so I do the inverse cosine of the arc cosine. So technically speaking, I would do the arc cosine of the cosine of x equals the arc cosine of positive negative a half. Arc cosine and cosine cancel out. I'm left with x equals. And now it's time to answer the question. So I think this is one I should know. So I'm going to draw a circle. And I'm going to identify all of the places where cosine is a half. So that's going to be when the x is a half. So notice it's positive or negative a half. So that means cosine, positives would be here, negatives would be here. And so my answer is pi over 3. My answer is 2 pi over 3. My answer is 5 pi over 3. Oops, 4 pi over 3 first. and 5 pi over 3. Okay, so if it only wanted the answer between 0 to 2 pi, then that's this answer. There are 4 answers. But once again, if I want all of the answers, I need to be at these locations and wrap around again and again and again and again. So once again, there's probably a shortcut. I probably shouldn't write this as 4 separate answers. And in fact, I think using our common sense, we can at least get away with doing 2 answers. So let's look at this. One of the answers is right here, which is pi over 3. This answer over here is 4 pi over 3. That is just pi away from the first answer. So I can say, at least to make it a little bit easier, I can say pi over 3, start there, and then to pick up the 4 pi over 3, I would just add pi. And how many times am I going to add pi? Because if I add pi again, I'm back at pi over 3. Add again and again and again. So if I add a pi repeatedly, but also subtracting pi will work. So we're going to say for every n, that is an integer. So we put our stamp on the end of it. And then I could say 2 pi over 3. That gives me the answer right here. And then this answer is 5 pi over 3, which again is just pi away because it's a straight line, right? So that's just half a circle. So plus pi n, and I can wrap it around as many times as I want. All right. Now, there's probably another way I could say this. This would be probably the ideal answer for like the C to B student. But the A student, I would expect to go a little bit further. The A student, I would expect you to at least put some effort into, can I just make one statement? Sometimes the answer is yes, sometimes the answer is no. So what do we notice here? All I'm doing is I'm adding a pi over 3. That gets me there. I'm adding a pi over 3. That gets me there. Ooh, adding a pi over 3, that doesn't get me what I want because I'm leaving off that 0 or that pi value. So it can't just be a matter of like just add pi over 3s around the circle. But let's see if we can use the same trick from last time. Notice that they are equally distant from here, and they're equally distant from here. So can I say that in one statement? I think the answer is yes. So on one hand, it looks like I'm saying if I start at pi over 2 and add or subtract pi over 6, so 60 degrees and 30 degrees. So if I want to be at the 60 degrees, the pi over 3, then I would subtract 30 degrees or the pi over 6. So that seems to get me those 2 answers. Well, all the other ones are the same thing from negative pi over 2. So I could just say from positive pi over 2, also from negative pi over 2, add pi over 6 and subtract pi over 6, and you will get all 4 answers. Then let's wrap around the circle from each of those locations. Two pi times. Put the stamp on the end where n is an element of the integers. This is your best answer. This is an okay answer. So always aim for the best, and if you can't really quite get it, then at least you've got a good answer, but see if you can get the better answer. All right, I'm going to run out of time before I do all 4 examples, but let's just do one more. Part B, and I think we're still going to be looking, let's kind of think of it as 2 parts. Let's answer the question for all x, but before we do that, let's answer it for once around the circle, because that's really how we're going to help us get all of the x's. Algebra-wise, I'm going to subtract 1 and divide by the square root of 2. So I should be looking at sine of x equals negative 1 over the square root of 2. I'm going to take the arc sine of both sides, which leaves me with x equals the arc sine of negative 1 over the square root of 2. I'm not going to rationalize this because I'm not reporting an answer here. We only want to rationalize necessarily when we're like all the way done. So leaving it here is fine because this is not my answer. So then I just have to ask the question, once around a circle, where is sine, God, I can't make it any better, where is sine negative 1 over the square root of 2? And hopefully this is conjuring up pi over 4s for you. But in the negative location, so arc sine would technically return this value of negative pi over 4. But this angle over here, as crappy as my circle is drawn, would also have the same sign. And so we have an answer of, if we're going to look around the circle from 0 to 2 pi, right? So if we're going to give this answer, then one answer would be all the way to here, which would be what? 5 pi over 4? So the answer would be 5 pi over 4 and 7 pi over 4. And that's if I'm thinking about going around the circle one time from 0 to 2 pi. Technically, arc sine gave me this answer of negative pi over 4. But again, ultimately speaking, remember that arc sine is just a tool to get us going. Like, what angles are we talking about? And then it's our job to figure out, okay, where do they fit into this system? Okay. So how am I going to answer this for all values? Well, it looks like if I start right here, I can go pi over 4 this way, and I can go pi over 4 that way. So the best answer would be, let's say x is going to equal, and you can either start at 3 pi over 2, or you can call it negative pi over 2. I'm going to add, and I'm going to subtract pi over 4. Once I get to those two locations, which is what this says, then I can take each of those locations and wrap it around multiple times, where n is saying, oops, wrong hieroglyphics. Come back, marker. Thank you. What's an n for all n's that happen to be integers? This would be my best answer. An okay answer would be just to answer them separately. And I could say x is going to be, you could either do it in the, I wouldn't care. You could either say it starts at negative pi over 4, or you could call that 7 pi over 4. I do not care because we're going to wrap around both directions and hit that value either way. So I'll just use the shorter version, negative pi over 4 plus 2 pi n for all the n's that happen to be integers. But I would also have to then describe the other one, negative 3 pi over 4 plus 2 pi n, where n is an integer.